to all of you. In this lecture we will discuss about the smart grid protection. In one of our lecture we discussed the relaying practice, basically the digital relays are adopted for the protection of the system or power system, and as you know that this electromechanical relays are not anymore in use and we are moving towards smart systems. So, in that case we have to use the digital based relays. And in this lecture mostly we will focus basically issues and protection of the smart grid system. So, what are the protection issues or difficulties are present due to the integration of renewable sources? One by one we will discuss, and after that we will go for basically the operation of the overcurrent relay, and along with that also we will discuss about this directional overcurrent relay operation which are used for protecting this smart grid or microgrid system. Now, coming to this particular part of this figure, you can see that we have this portion is our microgrid, here it is, and this portion is our macrogrid. This macro means our grid side, grid system, and this is our microgrid means we have this renewables, we have batteries and we have loads. If any fault occurs, let us say at this grid side, I mean this microgrid side, then those protection devices are going to take care for this particular fault, so that this fault should not propagate to the healthy sections of the network. You can see we have these symbols, we have used this VCC, and G is the storage, and also we have static switch SS, this CB stands for circuit breaker, MC is basically the micro source controller, and also we have this CC, the central controller. You know, this in smart grid system we are designing a central controller system, and also we have local controller system. So, what will happen, the protection devices will also share the data with the central control station, and from there again we can take some decision which will be more accurate and reliable for the proper or smooth operation of the microgrid system. That is what this CC, the central control system, does. And if you can see, the CC is present here, and the red dotted lines are basically the information coming from the protection part or protection infrastructure, you can say. And this protection infrastructure is almost collected, this is connected to all the parts of the network. This red dotted line you can see here, this is our, this MC is basically the micro source controller. This MC is present near to our renewable energy source, and this MC also communicates with the CC, and as well as this particular you can see here the corresponding circuit breaker. This is our sectional circuit breaker present here. The sectional circuit breaker also talks to our MC. So, we are also planning, see in some time, I mean the time will come that all the devices are going to speak to each other. That is what we are aiming for smart grid system, and this aim of this particular subject is basically the basic concept we are just providing here. We are trying our best to give some idea that what will be our near future system, where you will see that all the components will speak to each other, and finally at the central control level or at the local controller level we can take our decision quickly, and very fast decision can be also possible with our very dedicated communication infrastructure. And you can see that if any fault occurs, this protection system will try to isolate very less number of sections. I mean it will just affect only the faulted section, not the other healthy sections. That is what the protection system aims. Now, if you have some fault at the grid side, then also we have to check this, also we have to take care for that. Otherwise, this fault current will propagate to the microgrid parts or microgrid components like renewable sources, like we have battery storage, we have loads, even also storage also we have in the microgrid side or grid side, but still those components are basically very sensitive electronic devices. So, we have to basically restrict the fault current should not, I mean the fault current should not flow from the grid side to the microgrid side. That is what also another issue. I mean, we have to take care this utility grid fault should not propagate, fault current should not propagate to the microgrid side. These are the issues you can see. The first issue is the dynamics in label of fault currents, that is the first issue. We will discuss one by one the subsequent PPTs. The second one is the bidirectional fault current, and third one is fault stripping, and the fourth one is blinding of protection. These are the protection issues as far as the microgrid is concerned. If you are going to integrate solar based DGs, or we are going to integrate a wind system, or we are going to integrate like synchronous based DGs, that is small hydro power plants, to our distribution network, then how this protection system is going to be affected. The first one is dynamics in label of fault currents. I have taken this particular figure or system. This is our main grid, and this is DG1, and this is our DG2. Now, if any fault occurs, like one fault, let us say, is present here, then this current and this IGF, the fault current is going to be driven by this grid, and also fault current will be contributed by this G2, and also the fault current is going to be contributed by this G1. This G1 and G2 are two renewable sources. Now, finally, this fault current IF is the summation of IGF plus IG1F plus IG2F. So, this is basically the one scenario when this is a grid connected mode of operation. Let us say now the grid is disconnected from the rest of the network due to the opening of the circuit breaker. That means, this two DGs, two renewable sources, are disconnected from the main grid. In that case, what will happen? So, in this case, the fault current is equal to summation of only these two currents. There is no question of this IG, the grid current IGF, I mean this capital G, this IGF is equal to 0. That is why this fault current is summation of IG1F plus IG2F. So, the conclusion here, I mean the discussion says that during fault, the fault current label during different mode of operation, this fault current label changes, and also based on the type of this particular grid integration, like mode of operation, whether the microgrid is connected to the grid, or it is in islanded mode of operation, or two DGs are present, or one DG is present, how many loads are switched on, switched off. Based on the different type of mode of operation and network configuration, the label of fault current changes. And apart from that, based on the type of DG integration, if we have like inverter based DG, if any fault is incepted, then the fault current is going to be clamped to 2 per unit of the rated current. If it is basically synchronous based DG, then the fault current is going to be 5 times of the rated current. So, these are basically the concerns, basically the dynamics of the fault current label changes as far as the penetration of the DER is concerned, or the magnitude of the fault current also changed due to this different modes of operation of the microgrid or smart grid system. So, these two are the major reasons due to which this fault current changes. Now, we have another concern, that is the bidirectional fault current. Like see this particular picture, here you can see this is a low voltage bus, and here we have this DG, and here we have loads, and this is the fault point. To this fault point, the fault current, if this fault is F1, I will just designate the fault current which is contributed by this DG in left to right direction. The direction is from left to right. But if this fault is at this LV bus or grid side bus, then this DG will contribute in right to left direction. That means, the direction of the fault current contributed by this particular DG differs based on the location of the fault with respect to the DG location. That means, in this case you can just memorize that in case of distribution system, mostly we use this overcurrent relays, and in mesh network we use this directional overcurrent relays, where the direction of the fault current is a concern. Nowadays, as these renewables are penetrated to the distribution network, so the fault direction is changing. So, that is why only the overcurrent relay is not sufficient. We have to also add the directional unit along with the overcurrent unit. That is what this bidirectional fault current issues basically tells us, that we have to use this directional overcurrent relays, not only overcurrent relays. Another issue is that is false tripping. So, what is this false tripping? Here is our main grid, right. If we will take this example, it will be easier to understand. So, that is why I have taken this particular picture or figure, a small microgrid system where this is our main grid and this is a PCC, point of common coupling, and this is the distribution transformer, and this is a circuit breaker of the main grid side. These are two feeders, feeder 1 and this is feeder 2. Here is load present and here is one DC connected. Now, if any fault occurs, like one fault is incepted in feeder 2, then what will happen? This DC is going to contribute current to this fault point, and the main grid also will contribute some current to this fault point. So, there are two fault components because there are two sources. So, obviously, we have two fault currents, right. So, this IF will have this I DC plus I grid, two fault currents, because the load is not going to provide any current. What will happen here? This R1 is basically protecting, this is R1 is one relay, overcurrent relay you can say, is protecting this particular feeder, feeder 1, and this R2 is protecting feeder 2. Now, you know this feeder 2 is basically the faulty section, the feeder 1 is not the faulty section, right. So, it is not necessary to disconnect feeder 1, it is necessary to disconnect this feeder 2, right. So, what will happen? Due to this fault, this relay R1 will see this IZ or IDZ amount of current, that is also fault current, you know, when there is some fault, the fault current magnitude increases. Now, due to that, this particular fault, due to this particular fault, this R1 is going to trip, it is an, if it is an overcurrent relay, because this fault current magnitude may exceed the threshold value I set. So, that is why we are just if we can add one directional unit here, this directional unit, then we can say that no, there is no fault in this healthy feeder, right. There is better, we can say there is a fault in feeder 2. So, in this process basically we can solve the protection issues, that is one of the false tripping. This tripping of this R1 relay is known as false tripping. Now, we have another issue, that is a blinding protection. This blinding protection means what is that? In case of microgrid system, let us say we are integrating many number of DGs throughout the feeder, then what will happen to the fault current label or resultant fault current? That is what the blinding protection says. Let us take this particular picture. Here we have this main grid and one DG is connected here and the main relay is located near to this substation. Now, a fault is created at this bus. For this particular fault, the current which is contributed by this grid is IGF. This IGF is fault current contributed by the grid, main grid. Now, and this IG small IGF, that is the fault current contributed by the DG or DR you can write, right. So, what will happen now? Initially this fault current, if suppose there is no DG, without the presence of DG, this IGF is going to be 0, right, because if this DG is not present, so obviously this IF is equal to completely contributed by this grid, the main grid IGF, right. Now, if this DG is penetrated and DG is present, now this IF is equal to IGF, this capital GF plus small IGF, the current contributed by the DER or distributed energy resources. Now, if this is absent, this Ig, based on this particular IGF, the relay setting, if it is an overcurrent relay, this overcurrent relay setting is done. The setting of this particular relay is based on this I capital GF, the current fault current contributed by the grid system. But however, now due to the integration of or penetration of this particular renewable source, what will happen, this Ig, this small IGF is going to be contributed to the fault point. So, as a result, this Ig will be less, this fault current will remain constant even if we integrate 2-3 number of DGs. So, to meet this particular IF, this Ig, this let us say Ig dash after connecting this DG is this magnitude will reduce in comparison to your IGF. If we can just write this IGF dash, this is the grid is contributing the fault current after the connection of the DC, and this magnitude, the fault current magnitude is less than this IGF. This IGF is the current contributed without the connection of the distributed energy resources. Now, this is if this is the case, if this current contributed by this grid side due to the integration of this DG is basically decreasing, that is why that means the fault current is falling below the set value of the overcurrent relay, and then the relay is not going to respond. Relay is now blind, it cannot see the fault which is incepted in front of it. So, this property is known as blinding of protection. Again I am repeating that due to the integration of this DG, to meet this fault current, this grid side source would supply some current, and that current magnitude is less than the current magnitude which is due to the without integration of the renewable sources, and as a result this fault current may fall below the setting value of the overcurrent relay, and this property of the relay is known as blinding. Now, the relay cannot declare whether there is some fault in front of it. This property is a very important issue as far as the smart grid or microgrid protection is concerned. Now, I will take this particular picture and what are the concerns or issues we have discussed previously, we will just give one example through this particular figure. This is our grid and this is one relay R1, this is relay R2, R3, R4, R5, R6. We are assuming here that all the relays are overcurrent relays, and this is one synchronous based DG and this is inverter based DG. This SB stands for synchronous based DER, means distributed energy resource, and this IBDR means inverter based distributed energy resource. Now, let us say we have created one fault here at the point F, right. Now, the fault current will be driven from all these three sources. This is source 1, that is my grid, and this is source 2, that is my inverter based DER, and this is my source 3, that is synchronous based DER. The three sources will contribute to the fault point. The fault current is going to rush to the fault point. Now, when this fault current will come, this previously we have discussed that synchronous based DER basically provides 5 times the rated current, and the inverter based DER provides 2 times 2 per unit, that means 2 times of the rated current, and it clamps due to the presence of the electronic parts like IGBTs. This particular it clamps to 2 per unit, otherwise that is just for the safety purpose of the inverter, it is a property of the inverter. It clamps this current to lower level, right. So, but in case of this SBDR we do not have any inverters, right, that is basically synchronous machine only. So, what will happen, this more that the current which is contributed by this SBDR is more than this IBDR, and that is what this IFSBD is the current contributed by the synchronous based DR, and this IFIBD is the current contributed by the inverter based DG. Now, if you will see, due to this what are the issues are coming up. Let us see the first issue, the dynamics in level of fault current is seen in relay 5 R5. This R5 will see huge amount of current, that is 5 times of the rated current. So, that is what this, if this relay is not properly set, or we have to keep proper setting, so that the relay will basically should trip properly. That is the first. Let us say if previously we have this IBDR type system, then obviously this fault current which is going to be contributed, and the fault current which is seen by this R5 will be 2 times of this I fault, I rated, right. So, in this case we have to basically change the settings time to time, and this kind of system is known as adaptive setting of the overcurrent relay. Now, coming to the second point, this fault stripping is seen by this R4 and R3. R4 is here and R3 is here, because you know this fault is present here, whereas this section, this line is a healthy line, healthy section. However, due to the contribution of this fault current, this R4 and R3 may trip if it is not directional in nature. That is what I discussed in the previous section, that this is known as fault stripping. Though there is no fault in this section, but the current magnitude is higher, which may exceed the setting value of these 2 relays R3 and R4. So, therefore, these 2 relays should be embedded with directional unit along with the overcurrent unit. These 2 relays should be directional overcurrent relay. Now, the third one is the blinding protection. The relay R1 and R6 will see the blinding protection. This is our R1 and this is our R6. Why this R1 will see the blinding protection? Because due to the integration of the DGs, the fault current will be also contributed by these 2 sources along with this grid system. Let us say previously, if you will assume that these two renewable sources are not present. So, what will happen? The fault current only it is going to be contributed by this grid, that is IF grid. Now, let us say due to the integration of these 2 DGs, the fault current is going to be contributed, I mean the fault current is summation of these 3, that is your IF grid, IF IBD and IF SBD, right. So, due to this, the contribution of this fault current IF grid, that is it will reduce, is less than this IF grid. If this is particular the fault current, you can say that with integration of DR and this is without integration of DR, and that is why this relay R1 current will be reduced. It may fall below the setting value of the relay R1, and this is known as the blinding protection issue of the smart grid system. So, today in this class we will just summarize that we have discussed the protection issues of the smart grid system. The first one, we discussed the dynamics in the fault current. There is a change in fault current due to the penetration of different types of DERs, and also this dynamic of the fault current depends on the mode of operations, whether the grid is microgrid is operated in grid connected mode or it is in islanded mode of operation. Now, next we discussed that due to this integration of the renewables, the fault current direction may change, right. The bidirectional power flow will be there, and the third one we have discussed the fault stripping issues, and the fourth one blinding and the protection. Thank you so much.